I can't hear your voice, but your face, but I can see you.
Yeah.
Okay.
Try different.
I can hear now. Okay. I think it's because now is at EM in sorry, maybe in Oxford here, and 2 p.m. here. Can we start now? Atkins-nya hilang. Atkins-nya hilang ya. Oke. Ya, hilang. Oke. Aduh, tolong bisa. Ya, barusan dia lift, kemudian dia hilang lagi. Aduh, sebentar. Dia nggak bisa di. Okay, can you unmute? Unmute. Okay, okay. Okay, but I can't hear your voice. Okay, now it's okay. Okay, now it's okay.
Okay.
Yeah, thank you very much. Can we start?
Okay.
Okay. Okay, thank you. Pak Saur, monggo Pak Saur. Pak Saur.
Yeah. Hello. Can you hear me? Pak Adi?
Yes, yes, yes.
Oke. Saya mulai sekarang?
Ya, ya, silakan.
Tidak sesuai dengan yang dijadwal?
Sudah. Sekarang sudah jam 2. Oh.
Oke. Oke. Ya. Halo, Mr. Atkins.
Hello. Hello.
Halo, Mr. Atkins.
Atkins.
Halo.
Hello.
Halo,
Yes,
Mr.
hello.
Atkins. Oke. Iya. We will start our lecture. Yeah, I want to say you good morning. Good morning, Mr. Atkins.
Good afternoon.
Morning.
Good afternoon to you.
Yeah, our honorable speaker, Mr. Peter Atkins. Good morning in UK. Good afternoon, everybody. My colleagues in Indonesia and my student in Diponegoro University. Also the student for anywhere in Indonesia. I'm greatly honored and pleased to welcome to this afternoon for our JKSA webinar series on chemistry organized by JKSA Journal with the special our excellent guest and speaker, Peter Atkins. Welcome to this webinar, Mr. Peter Atkins. Thank you for joining and sharing your valuable time, knowledge, and experience. All participants, please give your deeply applause to our excellent guest and speaker, Peter Atkins. Okay, thank you very much. Yeah, ladies and gentlemen, I am very pleased as a moderator of our speaker, Mr. Peter Atkins. My appreciation to JKSA committee. My name is Parsauran Syahan, lecturer of physical chemistry, chemistry department, faculty of science and mathematics, Diponegoro University, who teach quantum chemistry, especially applied for intermolecular interaction. And sometimes I do by computational calculation. Now, I'm very pleased to introduce our excellent guest and speaker, Peter Atkins. I just read from his 11th edition Atkins Physical Chemistry book, published at 2018, Mr. Atkins. Yeah, I got this book from my brother as a present that he bought in USA. The 10th edition also I got as a present from my supervisor, Dieter Giso from TU Berlin. Thank you to them. For the next edition, I hope I will get as a present for our greatly honored guest and speaker, Peter Atkins. Hello. Yeah, maybe just kidding. I'm sorry. I digress. I will continue. Peter Atkins is a fellow of Lincoln College, Oxford, and was professor of physical chemistry in the University of Oxford. He is author of over 20 books for student and general audience. His texts are market leader around the globe. He was the founding chairman of the Committee on Chemistry Education of International Union of Pure and Applied Chemistry and was a member of UPEC Physical and Biophysical Chemistry Division. Ladies and gentlemen, now let me give time to Mr. Peter Atkins for 15 minutes to convey his lecture with the title, The Origin of the Law of Nature. We have time for 40 minutes for question and answer. Participants can submit question in chat box. Please, Mr. Atkins, time and screen are yours.
Thank you. Thank you very much. I will share my screen. I will moment. Sorry.
Yes, I can see your screen share, Mr. Atkins.
Yes. One moment, I shall try to get a different. Let me right, can you see my screen satisfactorily?
Yes,
We
yes.
can.
Okay. Well, today I'm going to talk about the origin of the laws of nature. We know that a great deal of events take place in the world around us, which I've summarized in the screen in front of you. But what scientists, of course, do is to look for organizing principles so that they can understand the events that are taking place. And they call these organizing principles the laws of nature. And as you see, I have a selection of laws of nature in front of you. What a law of nature really is that it is a summary. So experiments are done in the world and in the laboratory, and the accumulation of that experience is summarized by the formulation of a law of nature. And some of these laws are very important. I think the conservation of energy is probably the most important law of nature of all. But there are many other laws of nature, and I want to talk about their origin today. The world is a very beautiful place, but what scientists try to do is to understand that beauty in terms of the underlying processes that are going on. And people have speculated about the origin of the laws of nature. Philosophers and theologians often think that the laws of nature have been imposed upon the world at its creation. But scientists, in my view, look for simplicity. They try to understand the complexity of the world and the beauty of the world in terms of the underlying processes that are going on, in terms of the simplest possible interpretation. So what I would like to do is to see whether very simple ideas about the world can account for all the laws of nature. And I do mean all the laws of nature. So I shall adopt 3 principles which I think summarize towards simplicity. And I will make one hypothesis to underlie everything that I say. The principles are as follows. There is, first of all, indolence, laziness, doing nothing at all. Can I account for the laws of nature if I do absolutely nothing at all? So do they spring from indolence? And if indolence does not work, could it be that anarchy also summarizes the accounts for the other laws of nature? So allowing no laws at all, does a law emerge? And thirdly, if indolence and anarchy are not enough, can I show that being ignorant also leads to a law of nature? So what I want to argue today is that these 3 principles, that of indolence, anarchy, and ignorance, are sufficient to account for the laws of nature. And the hypothesis I shall make, the underlying principle, concerns what happened at the origin of the universe. And there is a summary of the history of the universe from the moment that it was created to today. And obviously this is an average over all our histories, but it summarizes what has happened to the university since it was formed. Now, it may be that the universe has given rise to daughter universes. So this universe sprang from the original universe. This universe sprang from this universe. And this may be our current universe, with the laws of nature springing from the laws of nature in this universe, and the laws of nature in that universe springing from the laws of nature in the original universe. But of course, it might be that we are in this original universe, and that is what I shall suppose today. And I shall focus attention on the origin of this universe. What happened at that moment? How did the laws of nature come into existence at this initiation of the universe? And here is a picture, nothing on the screen, of what there was before there was a universe. There was absolutely nothing. And I want to talk about the properties of absolutely nothing, when I will call it absolutely nothing. At that moment, there was no space, there was no time, and there was nothing at all. And what are the properties of nothing at all? Well, it is totally uniform, and I shall represent total uniformity by this illustration. So you cannot have absolutely nothing that varies from place to place. So I want total uniformity before the universe began. It is also totally isotropic. That is, if you go around any point, then the universe does not change. Absolutely nothing is totally isotropic. And thirdly, the final property of absolutely nothing is that it is totally empty. And I shall represent that by this icon. So the universe was totally uniform. Before it came into existence, absolutely nothing was totally uniform, totally isotropic, and totally empty. And my hypothesis is that when the universe came into existence, it inherited the properties of absolutely nothing. So at the instant it came into existence, it inherited the properties of uniformity, isotropy, and emptiness. And then, of course, there was the Big Bang, and everything took off from there. And we have our current, very, very complicated universe. So what happened is that the properties of uniformity were inherited when it came into existence. Bear that thought in mind as I give my talk. What is the role of indolence? What is the role of doing absolutely nothing? The first law I shall talk about is the most important law of all. It is the conservation of energy. Everyone is familiar with what that means. In very simple terms, it means that if you throw a ball in the air, then of course it loses potential energy, it loses kinetic energy, it gains potential energy, and then as it returns, it gains kinetic energy again. But the total energy, of course, is constant. On a much bigger scale, the conservation of energy is very important because it acts like a policeman in the universe. Nothing can happen that does not conform to the conservation of energy. And once you have a conservation of energy, you have the possibility of understanding the universe. And once you have the possibility of understanding the universe, then you have the possibility of science. So the conservation of energy really underlies the existence of science and everything that we as scientists do in our daily activities. But where did the conservation of energy spring from? And that is what I want to address. And to do that, I shall return to one heroine of mine, who is the German mathematician Emmy Noether. Emmy Noether proposed a very important theorem that I'm going to introduce. She was also unlucky. In my view, mathematicians die either close to zero or close to infinity when they are very old. Emmy Noether was unfortunately in the former group, and she died young, but still had done a great deal of very important mathematics before she died. And the theorem that I want to mention is that Noether's first theorem, I will perhaps come to her second theorem later. But Emmy Noether's first theorem was that whenever you have a conservation law, then you have symmetry. So to account for a conservation law, you have to look for an unrelated symmetry. Now, in particular, when you have the conservation of energy, so that energy does not vary with time, the underlying symmetry, according to Noether, is that time is uniform. So if time is uniform, then energy is conserved. That means to account for the conservation of energy, we must look for the origin of the uniformity of time. If time is not uniform, if it goes tick, 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 like in some lectures, then energy would not be conserved. So what we have to do is to account for the conservation of, for the uniformity of time. And that takes us, of course, to what I said previously, that if absolutely nothing is uniform, and the property of uniformity is inherited when the universe comes into existence, then the new universe inherits the uniformity of time on a cosmic scale. And so energy is conserved. That means that we can understand the conservation, that law of the conservation of energy, by this principle of inheriting the uniformity of absolutely nothing. So there is why energy is conserved, because we have inherited the uniformity of nothing. The question that arises is how much energy there is in the universe. Is this the amount of the energy? Is this the amount of energy that there is? And is this the amount of energy? How much energy was created at the beginning of the universe? Well, to understand, to arrive at an answer to that question, we need to understand how much energy there currently is. Because whatever amount there currently is, there has been at the beginning of time, and was and will be for all time. So how do you measure the energy in the universe? Well, you weigh each galaxy, and you take its mass, and you multiply its mass by c squared, and you get its energy. And so we go back to the universe, we weigh this galaxy, we multiply its mass by c squared, and we get its energy. We take this galaxy, do the same, add it to the first energy, and get an even bigger energy. And so on, for all the energy of all the galaxies in the universe. And when we have measured the mass of every energy, of every galaxy in the universe, and we add in dark matter and dark energy, then we will get some huge energy. Where did that energy come from? Well, scientists are circumspect people, and they know that there is another contribution to the energy of the universe. That whenever two galaxies interact gravitationally, their energy is lowered. So allowing for this interaction lowers the energy of the universe, of the galaxies. And if I now go to the universe and allow and look at that huge energy, but allow for this galaxy to interact gravitationally with that energy, with that galaxy, the energy is lowered. Now I allow this galaxy to interact with that galaxy, and once again, the energy is lowered. And you can see where this is going. If I allow for all the interactions between all the galaxies, then what happens is that the energy of the universe is lowered, I think, to zero. So there is no universe, no energy in the universe. Originally, there was no energy. Currently, there is no energy. And so none was created when the universe came into existence. And so philosophers and scientists no longer have to worry about where all the energy came from. There is none. Of course, there is positive energy and there is negative energy, but the total energy is probably, and I say probably, exactly zero. Let's go back to that conservation of that inheritance of uniformity again. Does it account for other laws of nature? Well, what about linear momentum? We know that linear momentum is conserved. And Noether's theorem says that to account for the conservation of linear momentum, we need to look at the uniformity of space. So when space came into existence, and as well as time coming into existence, it inherited the uniformity of nothing. And space became into existence on a global scale in a uniform way. And as a result of that, we have the uniformity of space, and therefore we have the conservation of linear momentum. What about isotropy? We saw that we saw that absolutely nothing before the universe came into existence was isotropic. According to Noether's theorem, if you have isotropic space, then you have the conservation of angular momentum. And therefore, there is another law of nature coming into existence because we inherit the properties of absolutely nothing. In this case, we inherit the property of the isotropy of absolutely nothing. So we know also that there is no angular momentum in the universe, because if we know that there is no angular momentum in absolutely nothing, but each galaxy is spinning, rotating in a different direction. And if we add together all the angular momentum of the observable universe, once again, we get zero angular momentum, which certainly suggests that when the universe came into existence, it inherited the property of absolutely nothing. So to put this more in a chemical context, when people Joule and Kelvin were establishing the conservation of energy by studying the conversion of work into heat, what they were doing, but did not know that they were doing, was studying the symmetry of space-time. So when you teach thermodynamics, you are actually teaching the properties of space and time. Let me go on to the role of anarchy. What is the role of anarchy? Well, I will talk about a group of ideas springing from this group of people. And in particular, I will talk about the propagation of light. Everyone knows that in a uniform medium, light travels in straight lines. More precisely, light travels by the path that takes the least time from its point of origin to its point of detection. But how does light know that this path will take the least time? Suppose it made a mistake and started out by this path. It would take even more time for it to go back and correct itself and take this path. So how does it know that this is the path of least time and not take this path? Well, I think it takes that decision on the basis of its intrinsic nature, which is that of an electromagnetic wave. So if you have a wave which travels along this path, then light will end up with a certain phase at this point. But suppose it took a neighboring path, then it would end up with a slightly different phase. Let me exaggerate that by showing the difference in phase, if you can see that. The phase arriving at this point is quite different from the phase arriving at this point. And of course, if it took yet another path, then the phases, there would be many different phases at this point. So many different phases, in fact, that all the phases would interfere destructively. And you would conclude that light did not travel by any of these paths. But suppose it traveled by a straight line path, then that path has a neighbor which gives it a phase very similar to the phase on the original path, which I can represent like that. And any other neighbors near that close path also have phases that at this point that are all very similar. So all the light coming by paths close to the straight line do not interfere destructively. They survive. So if you allow anarchy, if you allow light to travel along any possible path between this point and that point, then because the curved paths all have neighbors that interfere at this point, they wash themselves out. They destructively interfere. And only the straight line path survives. So the origin of the law that light travels by the path of least time is actually anarchy. You allow every possible path, but only the path that you interpret as a straight line actually survive. Now that idea passes on, I don't know if you can see my screen fully, to the propagation of matter. Of course, here is an electron before, or any particle before 1927. After 1927, it became a wave. And of course, see how I have drawn the wave. Many people just draw a wave as an undulation. But when a particle has an actual direction of movement, you should really draw it as a helix, as this helical wave, because the direction of travel of the particle is given by the direction of travel of that wave. So this is an electron now. This was an electron before 1927. And of course, all you need to know is that quantum mechanics tells you that if a wave has a big amplitude, then the particle is likely to be found in that region. If it only has a small amplitude, then the particle will be found with low probability in a region. And if it has zero amplitude, then the wave will not be found in that amplitude, in that region. Now you can see that the argument I gave about the propagation of light applies equally to the propagation of matter, because once you realize that a particle has wave-like properties, then the argument about all these bent paths having waves that interfere destructively at this point means that a particle does not travel in the absence of fields by curved paths. A particle has this wave motion, and so it has neighbors that interfere non-destructively at the origin. And so we now account for the propagation of particles. Once again, if you allow a particle to travel by any path at all, then because curved paths have neighbors that interfere, we never detect these paths. All we see are paths close to a straight line. And this means that the principle of least action, which is what I've been talking about, springs from anarchy and leads, of course, to the classical mechanics of Newton. So we can now understand that classical mechanics springs from the quantum mechanics and the wave character of particles. And ultimately, it springs from anarchy. So if you impose no laws on the propagation of particles, then you end up with classical mechanics and indeed quantum mechanics. They are exhibitions of anarchy. Let me turn to something else that is related to this. Notice that this wave for an electron now tells me the probability that the electron is present in a region. But let me talk about its gauge. And a gauge is simply a measuring rod. So I'm going to introduce you to gauge theories. Gauge theories are the origin, these are a part of the theory of the origin of fundamental forces between fundamental particles, which is a part of the origin of the fundamental forces that I now want to talk about. And that means that I have to introduce you to gauge theory. But gauge theory is very simple. It simply says that if I take a wave and I change its phase, so I change the position at which I am measuring its amplitude, its phase from, then because the amplitude change does not change anywhere, the probability of finding the particle does not change anywhere. In other words, the theory is so-called gauge invariant. Nothing changes physically when I change the gauge. I can choose any gauge I like. I still find the particle with the same probability in the same region of space. That we say physics is gauge invariant. And now consider a small region of space and an electron traveling through it. If I change its gauge from blue to yellow, the probability of finding the electron inside the box does not change. In other words, the charge inside that box remains the same. In other words, gauge invariance, global gauge invariance, changing the whole wave, implies the conservation of electric charge. So once again, we see that out of absolutely nothing, because this can start at any point, we get a major law of nature, and a law that we know to be true. Before the universe came into existence, there was no electric charge. After the universe came into existence, there is positive charge and there is negative charge. But we know that there is an exactly equal amount of positive and negative charge. And so the total charge remains 0. We know that because the strength of the interaction electrostatically is much greater than the strength of gravitational attraction. And if there was an imbalance of charge, then the universe would blast itself apart before gravity had a chance to form galaxies. But there is more to it than that. Suppose I take this wave, and instead of changing its phase by the same amount everywhere, I change it, and this wave, of course, satisfies the Schrödinger equation. Suppose I change it by a different amount everywhere. I change it by a big amount there. I change it, well, so this is a uniform change. But if I change it by a different amount in different regions of space, a little bit of phase change there, a big amount of phase change there, nothing changes physically because the amplitude remains the same. So the probability of finding the electron in a region of space remains the same. But this new wave, the yellow wave, with its changing phase in different regions of space, does no longer satisfy the Schrödinger equation. It satisfies the Schrödinger equation with an additional component. And amazingly, the additional component is in fact the Maxwell laws of electromagnetism. So once again, to conserve local gauge invariant, if local gauge invariance is conserved, you get the laws of electromagnetism. And of course, out of that, we get the modern world of electromagnetism. So everything around us electromagnetic springs from this local gauge invariance. Now, I could talk about the role of ignorance. I will go faster here because I see I'm running out of time. I could talk about Hooke's law and the gas laws as springing from ignorance. But I want to talk about the most important of all the laws that spring from ignorance, which is the Boltzmann distribution. If you imagine Boltzmann throwing molecules onto the available energy levels, then one possible outcome is, of course, that possible outcome. But it is an outcome with very low probability. If instead you throw the molecules at random onto the available energy levels, but this is a much higher probability of getting this distribution, but it is still only a low probability. But if you, after with trillions of times, get that distribution, this turns out to be the most probable distribution of all, This is the one that, throwing molecules randomly onto the available energy levels, gives you most probably this distribution, which of course is the Boltzmann distribution. And so if I were confined to a desert island somewhere near your own country, maybe, then I would end up, I would like to have Boltzmann, at least the Boltzmann distribution, as my intellectual companion, because it accounts for so much. It accounts for the concept of temperature, because you get this distribution when this parameter T has a high value, and you get this distribution when the parameter T has a low value. And of course, it accounts for all the processes of chemistry. It accounts for stability when the temperature is low, because molecules in these states survive, whereas molecules in these states do not. And if the temperature is low, then it accounts for the stability and structure. So not only does the Boltzmann distribution account for reactions, it accounts for structure and is the underlying law, really, of physical chemistry. And it springs from randomness and ignorance. Now, I want to talk also about the processes that are going on, and to introduce, of course, well, my favorite law was the second law of thermodynamics. And everyone knows, really, that this does not happen. Things do not form structures automatically. What happens, the natural process of change, is, of course, for things to get worse. And of course, the second law of nature simply says that the world is getting worse. There's plenty, of course, examples of that sort of process. But things can get worse in a very interesting way. And when I teach the second law of thermodynamics, or tell the general public about it, I like to use this illustration, which summarizes a region of order naturally becoming a region of non-order, disorder. But if you have a mechanism that can tap into this process, then that mechanism might be able to drive the emergence of structure from disorder. So providing the loss of order here exceeds the gain of order here, then this order can emerge. So if this is an internal combustion engine and this is a fuel, then of course when it burns, it degrades into carbon dioxide and water molecules which disperse, and the energy released in this process disperses. And the actual engine, the actual internal engine, internal combustion engine, captures that energy and can be used to drive this process. This process might be a pile of rocks, and the structure that emerges might be a cathedral. So provided more order, more disorder is created here than is decreased here, then this process of creation can occur. And of course, that applies very generally. This might be breakfast. This might be the digestion of our breakfast. This might be the sequence of metabolic processes going on in our body. This group of disorder might be amino acids, which are built into proteins. So as we grow, as we eat, so we grow. And provided we generate more entropy here, then we decrease entropy here, then structures, living organisms can emerge. So once again, here is another example of a law of nature, in this case, the second law of nature, emerging from absolutely nothing. So we can actually now trace really the processes that go on around us. There is the process of nuclear fusion on the sun, and the dispersal of the energy that occurs. It's dispersal through the solar system. It's capture on Earth and the driving of photosynthesis on Earth by the process that I have just described. And then our use of the biosphere, our emergence from the biosphere, because we consume what has been created by photosynthesis in another process which depends upon the dispersal of energy. And of course, the emergence from the biosphere of brains that are complex enough to discover the laws of nature, and now, of course, to understand their origin. So let me come to a conclusion and summarize what I have been saying. In the beginning, before there was anything, there was absolutely nothing, not even space-time. When space-time came into existence by processes that currently we do not understand, then the newly formed universe inherited the laws of nature, inherited the uniformity of absolutely nothing. And out of that, discovered that by inheriting that uniformity, it could account for all the laws of nature. So let me conclude on that point. I hope that those of you who teach science now see that the origin of our understanding is indolence, it's anarchy, and above all, it's ignorance. And I think ignorance is a wonderfully powerful attribute of our understanding. So thank you very much indeed for listening.
Thank you very much for your lecture, Mr. Peter Atkins. For all the participants, I ask you to write your question. And Mr. Danmar, please help me to show the question for the participant. And I ask Mr. Peter Atkins can answer the question of the participant. Please, Mr. Atkins, I think you
Yes.
can read the question.
Yes, I can't read the entire question. I know this. That's better. Okay. Well, Max Tegmark, in his mathematical universe, developed an argument that I had proposed 20 years before. And so I wrote to him saying, why did you develop the argument that I had presented 20 years previously and not mention that I had developed it? And I got no reply. So I was a little annoyed by that, frankly, because he did not acknowledge that I had thought about it. I think if you want to read my original account, then it is in a book called Creation Revisited, and which I published in 1983. And I review the theory in another little book more recently called constructing the universe, conjuring the universe. And I think it's a very important idea that the universe is mathematical, because it explains why mathematics is such a powerful device for understanding and formulating the laws of nature and making and arriving at an understanding of the universe. And that suggests to me that the universe is actually mathematical in nature. And so I have argued in many places that the universe is based upon mathematics. And I don't have time to go into it in more detail at the moment, but some of my arguments are in some of the books that I have just mentioned. Okay, what is the final frontier in chemical science? Oh, there is no frontier. I think chemistry, like all science, is infinite in, well, let me be more careful. I think it is semi-infinite. I think it is finite in terms of arriving at understanding. So as we dig down into our understanding, we will arrive at a complete and final understanding. That's a very optimistic view, of course. But when it comes to applications, then I think it is infinite. So I think it is semi-infinite. Finite in the sense of that we will arrive at understanding, infinite in terms of application. And I suppose that the real challenge of chemistry, the most demanding, and it will take us perhaps decades, centuries to reach, is to use test tubes to build life of different kinds, real, conscious life, not just amoebas. What caused the Big Bang to happen? Well, if you go back to those books that I mentioned, especially Creation Revisited, I do talk about, in a very speculative way, how the universe began and how absolutely nothing could suddenly find that it was something. And I don't have time to go into that now. I could give another entire hour-long talk on it, but I think it was when the in very short order, I think it was when a point and not a point, as it were, two entities that were their opposites, discovered a topology. And as soon as there was a topology, the space-time could come into existence. That's a very quick, brief summary. But what I wanted to show is that although we don't know how it came into existence, it is possible to think scientifically about how it might have come into existence. Okay. So I've done those two questions. Which principle is the most relevant to be applied to identify and comprehend nature's beauty? That's a very good question. I think it's a combination of the first law, the conservation of energy, and the second law, the increase in entropy. I think the first law constrains and the second law allows. And I think the allowance of the emergence of entities under the constraint of the first law is, I think, the spring of beauty. Does that answer that question? What about gravity? Yeah. Oh, can it be said that before and after the creation of the world, the total energy remains the same? That, all the evidence points to that, provided by energy you include dark matter, dark matter, and dark energy. What about gravity? These are very clever questions, I must say. Yes, the mathematician Roger Penrose explored the still very perplexing connection between gravity and entropy. And he thought, in those days, still around, I'm glad to say, and this is just my neighbor in England, in fact. But he thought of a universe that expands, and if the universe expands indefinitely, then the creation of entropy is boundless. But he also thought that if by some instance the universe were to contract again, then the point to which it finally contracted could be a much more complicated point than the point from which it began. So topologically more complicated point than the original starting point. And because the complexity of that point was so great, the entropy could increase even though the universe was contracting to a point again. But now we know that the universe is not only expanding, but accelerating. And so the likelihood of it contracting again is very remote. But I agree, cosmological thermodynamics is still a very difficult and unknown field. Well, as in answer to what is the origin of energy, in my talk, I tried to show that if you add up all the energy in the universe today, there is none. So at the creation, none was created. The question that you should ask yourself is how it's separated into positive contributions and negative contributions. Positive contributions like kinetic energy and negative contributions like potential energy. So what science does, and this leads to a very important point, what science does is to simplify questions. So it no longer expects people to worry about where it all came from. It now worries about what I think is a much simpler question. How did it separate into positive and negative contributions? So science simplifies. It does away with very puzzling questions. Right, I think your last few slides, which are human brain in between leaves. Do you think the scientific mind merely resides in the bunch of meat we call brain? Absolutely, yeah. I mean, we materialists think that the brain is such a complex instrument, the most complex instrument that we know in the universe is capable of that most complex phenomenon, consciousness. And it's I think there are two, going back almost to, well, not quite the question that someone asked some time back, what is the frontier of chemistry? What are the two biggest questions in science? One big question is where it all came from. origin. And the second big question is the origin of consciousness within the material universe. And the wonderful science that we're currently doing is enabling us gradually to work towards answering these extraordinary, wonderful, and important questions. Right, where are we now? Can humans actually know what happened in the past? Then what is the true explanation of dark matter? Well, the true explanation of dark matter is to do experiments that study its properties, and those experiments are starting to be done. And there are clues about its form. And can we know what happens in the past? Well, history is a guide to the immediate past. Archaeology is a guide to the distant past. And cosmology is a guide to the very distant past. What I suppose one has to remember, is that science is a consistent web of ideas, like history and archaeology are both consistent webs of ideas. So you don't dig up a pot in Indonesia and think about it unrelated to a pot that was dug up in China. You think of it as part of the past and you look for connections between them. Likewise, you don't think of one scientific fact being isolated from another scientific fact. Science is a network of interrelated ideas. And so knowing the past means understanding, knowing the past, let me think, means discovering the network and seeing that it is consistent. So yes, we can know the past, provided we have discovered the network and see that it is inconsistent. If we discover inconsistencies in the past, just as an inconsistency in history means that we did not understand the immediate past, then in science it means that our theories have to be revised. Is there an exception of biological resistance to the rules of energy? What makes a death things can generate life? Is there any reason in chemistry and physics? Well, my view is that there are no exceptions. There might be laws to be discovered, laws relating to matter, but let's suppose that we know all the laws relating to matter, including radiation and all the forces. Then it is my belief that those will account for all the properties, including consciousness and the consequences of consciousness, which include aesthetics. What makes a death thing? Well, recycling, I'm afraid, that organisms die and feed the biosphere. So the biosphere ceaselessly, let's hope ceaselessly, we don't want it to come to an end, because that would be the end of everything we love. No, the end of life and the end of consciousness and the end of understanding. So let's hope the recycling, life, then death and re-emerging from life continues forever. Although, let me add to that, if we did create computers that could emulate consciousness without destroying the biosphere, then we could send them off to space without life support, and they could go on understanding forever. So I do think that an interesting question is whether the long-term future of human understanding is to be embedded in machines. Where are we? The four laws, yeah. Yeah. Well, why did the fourth law? It was an afterthought. It was realized that for consistency, for logical consistency of the laws of thermodynamics. Indeed, if you were to look at my little book called The Laws of Thermodynamics, the first chapter begins, the zeroth law was an afterthought. People realized they had formulated entropy in the second law. They thought that they had formulated its zero in the third law. They thought they had the first law and the conservation of energy. And then they realized they hadn't defined temperature. And what the zeroth law defines is temperature. So it is the logical precursor of the three. And of course, since they're already named 1, 2, and 3, zero. Another question on dynamics to be discovered is there a fourth law of thermodynamics? And I suppose there is a fourth law of thermodynamics if you were to include in thermodynamics non-equilibrium thermodynamics. But that's such a messy field at the moment. But if you, students among you, are looking to enhance thermodynamics, you might well find yourself discovering the fourth law of thermodynamics. Indeed, it occurs to me as I sit here, you might discover that there is a law even more fundamental than the zeroth law, in which case you will set yourself discovering the -1th law of thermodynamics. So next question. Sorry, I can't see my screen. Let me go to that one. Yeah, okay. Where are we? According to Big Bang theory, the universe was also anarchy before Big Bang kind of thing. Yeah. How do you explain consciousness in terms of energy? Well, I explain consciousness is a property of the brain, a physical property of the brain. And in particular, it's a physical property that emerges from the brain's structural complexity. So, and the structural complexity of the brain is an aspect of biology, molecular biology, and ultimately, therefore, chemistry, and I suppose ultimately physics. So, in a sense, I explain consciousness. I assert that consciousness is an emergent property of the physical entity we call that complex structure of the brain. There's nothing mysterious about consciousness. There's a lot that is wonderful about it, and a lot that, of course, we don't understand, but we're edging towards it. As we build computers that emulate parts of brain function, one day we'll bring them all together, all those parts, and we will find that we have an entity that it would be criminal to extinguish. How can the zero thought came up? Well, I've explained that. It just came late. Yeah. Have I answered all your questions? Yeah. There are some people who argue that the third law is not really a law of thermodynamics. The reason being, I think, I'm not quite sure, I think this is the reason. There's each of the preceding three laws, the zeroth, first, and second, introduces a new quantity, new physical quantity. The zeroth law introduces temperature. The first law introduces energy. The second law introduces entropy. And the third law doesn't introduce any new property of the universe. It enables you to do a variety of calculations because it establishes the zero of entropy. And that is very important when you come to think about Gibbs energy or Boltzmann energy and actually doing calculations with entropy. But it doesn't introduce a new property. And so some people think it's not quite a real law of thermodynamics. And of course, the third law of thermodynamics asserts that the entropy of all substances goes, of all perfect crystals goes to zero. And of course, we understand that statistically as well as macroscopically. So the thermochemical view is consistent with the statistical mechanical view. So another question emerging. There's one. We'll see that in a minute. Not quite on my screen yet. Can you share with us what conclusion can you take? What the most beauty of knowledge you have to learn? Yeah. Well, that's a very metaphysical question. I think I would say the greatest joy that I get comes from realizing that the universe is open to understanding, and specifically that understanding comes through the procedures that we call science, and that I think that understanding adds beauty, adds pleasure to beauty. Because although you can just look at something and say, that's beautiful, or listen to something and say, that's wonderful, that's beautiful. It's also possible for we as scientists, at least, to open the door to a deeper understanding and to add to the joy of understanding by understanding why we understand. So I think what I would regret most if the human race were eliminated before by whatever stupidity it entered into, then what I would regret most would be the destruction of understanding. Does a theory of everything exist? Not yet. You students out there will help to achieve it. If I'd like to create my own universe, what governing laws would you like to fix, change, or add from the current existing? It would be dangerous to change any law. Such is the network of the laws of nature, that changing one would have unforeseen consequences everywhere. So I would certainly change the laws that govern our behavior in to the roots of all. Could I share more references to about it? Yeah, look at, I have to suggest my own book, Conjuring the Universe. I don't have a copy to show you, but Oxford University Press, published in 2018, Conjuring the Universe, where I cover much of the material that I've talked about in this talk. Or I talk about there, for example, the origin of the values of the fundamental constants as well. So MC squared means that we kilograms for mass, joules for energy, and then therefore we have to have a conversion factor, c squared. If we had decided to measure mass in joules, the equation would be E equal m, and there would be no distinction between energy and mass. So matter is just localized energy. As a matter of energy coming from nothing. Yeah, provided an equal amount of opposite forms of energy come as well, as I try to explain in my book. Look at the reference. It takes the argument a little more slowly than I had time to develop today. But I think around us, there is still absolutely nothing. But it's an absolutely nothing, which is arranged into a much more interesting form than it was before the universe came into existence. In the physical chemistry book, my chapter about kinetics is tiny. Well, it's a pretty simple subject. I mean, the laws of chemical kinetics are well established. There's not much to say about them. There is something to say about oscillating reactions and chaos theory, which it depends where you draw the line in chemical kinetics. And there's a great deal to be said in terms of molecular dynamics. But in an undergraduate textbook, it's what you need to know is really the kinetic part, the simple laws, the first, second laws, and the various approximations which are due to explore them. It would be very difficult, for example, one of the problems, suppose we wrote a chapter on molecular dynamics and oscillating reactions, how would we examine it? I mean, it's very difficult to think of questions that can be written in a way that explores your understanding. So there's partial answers to that. How science can describe collective consciousness in the concept. I don't know what you mean by collective consciousness. I think societies develop ways of thinking that are uniform because they live in societies that demand kinds of uniformity. I don't think there's root. I don't think there's any Jungian collective consciousness. I see we're coming to the end of time, our time, if not the end of time. I think in due course we'll have conscious computers. We're moving towards it. I think the construction of a conscious computer. Let me go back to the answer I gave before. I think the answer to that great question about where it all came from will be found in mathematics and physics. I think the answer to what consciousness is will come from systems analysis and the ability to simulate consciousness on a computer, not necessarily digital computer, might be quantum computer, but I think it will be on the ability to simulate it. And if we know how we simulate it, then we will know something about its nature. I think I have to stop there. I think our time has come to an end. I hope I've covered what you wanted me to cover.
Hello, everybody. Any question anymore? Because our time until to 13:40, 15:40 Indonesian time. I think we just have 1 minute. Just 1 minute left. Mr. Atkins, I think it is time for us to say thanks for you for your nice sharing of knowledge. And I think for the participant, you can watch the YouTube because I have watched the YouTube for this, yeah. And some Mr. Peter Atkins. Is it right, Mr. Atkins?
Sorry, I don't quite understand.
Some slide, yeah, some slide. Yeah.
Yeah. Well, some of the slides might be copyright.
Okay, yeah. I think to get a good understanding, I hope you can watching YouTube, yeah.
Yeah.
Okay, yeah. Thank you very much, Mr. Atkins. For the participant, I think it is not so easy to understand what the lecture today, yeah. Because Mr. Atkins combined many laws, understand from nothing to, from absolutely nothing to something. Yeah, but this lecture, I think, inspired us to learn more and more, and try to understand the law that arrange the universe. Yeah, for example, many students don't like to learn about the Schrödinger equation, but I know the Schrödinger equation is very important, and I also here today, it is not enough just to understand Schrödinger equation. We have to combine with the Maxwell equation. Is it right, Mr. Atkins?
Yes, absolutely.
Okay, yeah. I think our time is enough. Thank you very much once more, Mr. Atkins.
Well, thank you very much for for listening to me.
We hope
it's a great pleasure to be able to travel so far without moving.
Okay, yeah, we hope we can meet again in other time. Yeah, and we hope we can you can share your really physical chemistry.
Yeah.
Yeah.
Good.
Okay.
Thank you very much.
Ya.
Goodbye.
Kepada peserta, terima kasih untuk partisipasinya. Luar biasa ya. Dan this time I really wait to meet Mr. Atkins. Yeah, I buy his book to learn, but it is not enough time to understand. But in every edition, will always changing. Yeah, also changing. The last changing, he changed from the chapter to the focus. I don't know why. Mr. Atkins changing chapter to focus. Yeah. From 10 to 11 edition. Oke, saya pikir begitu Pak Adi ya. Semoga ini bermanfaat. Once more, thank you very much to Peter Atkins. Have a nice day and have a good healthy also in COVID-19 situation.
Good.
I give back.
Okay, thank you very much, Professor Atkins. Thank you very much.
Thank you very much.
Thank you very much. Yeah.
Okay, I'll leave you now. So thank you for arranging.
Okay, thank you.
Bye.
Bye. Thank you very much. Terima kasih Bapak Ibu semua. Ya, nanti akan webinar berikutnya bulan depan hari Rabu pekan kedua ya. Setiap hari Rabu pekan kedua ada webinar yang diselenggarakan oleh Jurnal Kimia Sains dan Aplikasi, dan alhamdulillah hari ini kita bisa mendatangkan Profesor Peter Atkins. Saya hubungi 2 bulan lalu pakai email saja gitu, langsung direspon sangat baik oleh beliau, dan alhamdulillah hari ini bisa terlaksana. Terima kasih dan kita selamat sampai berjumpa bulan depan ya. Terima kasih.